Hello and welcome to the third Galvanizing TC webinar. I'm Ken Landau. I'm a staff engineer with AIST, and this webinar will feature accurate strip temperature measurement for continuous annealing and hot dip coating lines. As with all AIST functions, let me go through the antitrust compliances. Do not discuss with others your own or competitors' pricing procedures, or anything that may affect pricing, such as costs, discounts, term of sales, profit margins, or anticipated wage rates. Do not make statements about your own pricing or those of competitors, and do not talk about what individual companies plan to do in particular markets or with particular customers. AIST also has an anti-harassment policy, which is shown here. And some things to know. The attendee audio has been disabled. The questions to the presenter should be submitted via the Q&A feature. That way it will stay on this recording. The Q&A feature, if you hover over the menu for the Zoom, it shows Q&A. Again, that's where you want to do it. Myself and the moderator will see the questions and and the moderator will be able to present those to the presenter for answering. The session is being recorded and will be available on demand replay on our AIST website. Did you have any technical difficulties? You can contact us at training@aist.org. Another important reminder is photos recording of the presentation is strictly prohibited. You'll be given a link to access the presenter contact information and recordings following the end of the webinar. With that, I'd like to introduce our moderator, which is Greg Gutman. Greg, there he is from ISRA Surface Vision, ISRA. He's from Pittsburgh, has a BS degree in in computer science at the University of Pittsburgh. Greg currently works from ISRA Vision Parsitech, as an account manager for the metals business unit. In his previous life, Greg was employed in various capacities by General Electric, GE, Funuk Automation, Danieli Corp, Nidec, Abtron, Wonderware, VOC Gases, Mind Matters Technology, and Custom Industrial Controls. And now I will leave it to Greg to introduce our webinar presenter.
Thank you, Ken. Good morning, everyone. I have the pleasure to introduce Mr. Thomas Larrick, the Director of Technology of Williamson Corporation. Considered a leading expert in the field of infrared pyrometers, Thomas Larrick has been with Williamson Corporation for 33 years and currently serves as Director of Technology. Thomas has extensive experience supporting the steel industry. Prior to joining Williamson, he was a design engineer for General Electric Aerospace Division. He has a BSME degree from Tufts University. Ladies and gentlemen, Mr. Thomas Larrick.
Good morning and welcome. I'm going to be covering temperature measurement for infrared for continuous annealing lines. And today we'll be discussing infrared technology, welder measurement, continuous annealing measurements in the annealing furnace for the roller wedge, direct view measurement technique. We'll be talking about zinc-coated steel, galvanneal measurement, and the various zinc-coated steel measurement points. We're going to start by discussing a little bit about infrared pyrometer technologies.
Excuse me, Tom.
Yep.
Thomas, this is Ken. If you are not in presentation mode.
Oh, right. Okay. Thank you. Infrared pyrometers don't measure temperature directly. They measure infrared energy. And from this measured infrared energy, they calculate a temperature value. And one of the complications is that the amount of infrared energy emitted by an object is proportional to its temperature and to its emissivity. And it's this emissivity feature that makes infrared temperature measurement complicated. Emissivity is the amount of infrared energy emitted by an object compared to the theoretical perfect emitter at the same temperature. So emissivity is a percentage, but in practical terms, emissivity is the opposite of reflectivity. So a highly reflective material has a lower emissivity value than a non-reflective material. And emissivity can change. It changes with different alloys, different materials, different degrees of oxidation, different surface textures, and it can change differently at different wavelengths. And that's what makes the measurement in the continuous annealing furnace a bit complicated. So an infrared pyrometer under ideal measurement conditions, just about every infrared technology is accurate. But as soon as you introduce a complication, whether it be an optical obstruction, a background reflection, or an emissivity variation, or transparent target, then you need a specific technology to address the type of interference. In order to address these various types of interference, there are 6 different infrared technologies. 3 of these are single wavelength technologies where the pyrometer is measuring one specific wavelength band. And 3 of these are advanced infrared technologies where the pyrometer is measuring 2 or more wavelengths. For the single wavelength technologies, the short wavelengths are much more sensitive or much more accurate when we have a variation in emissivity or optical obstruction or misalignment. So what we see here is a graph that shows infrared energy versus wavelength. And as you can see, for various temperature values. So as you can see, as the temperature changes, the infrared energy changes much more significantly at the shorter wavelengths than it does at the longer wavelengths. And so when there's a variation in the amount of infrared energy that's measured, whether it be because of an optical obstruction or a misalignment or an emissivity variation, it's a much smaller temperature error when measuring at a short wavelength compared to a longer wavelength. And here we see the errors at different temperatures for different wavelengths. And these are the errors associated with a 10% change in optical obstruction, misalignment, or emissivity. And when you use a longer wavelength pyrometer, your errors are larger. And as the wavelength gets shorter, the errors become smaller. A shortest wavelength pyrometer, though, can only measure to a certain temperature, and it can't measure any lower. So if in order to measure a lower temperature, we need to scoot out to a slightly longer wavelength. And then that slightly longer wavelength can only measure so low. And in order to measure lower, we have to scoot out to a slightly longer wavelength. So the 3 different single wavelength technologies are long wavelength, short wavelength, and specialty wavelength. A specialty wavelength pyrometer is used to measure materials that are otherwise transparent. For example, if we wanted to measure the temperature of glass, or we wanted to measure the temperature of a gas or a flame, then we would need to choose a wavelength where that material was opaque. Long wavelength pyrometers are used to measure lower temperatures, temperatures close to ambient or even below ambient. So if we're measuring the temperature of a frozen food, we would need to use a long wavelength pyrometer because these short wavelength pyrometers can't measure such a low temperature. And then in the metals industry, when a single wavelength pyrometer is used, always, 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 it should be one of these short wavelength pyrometers. But what happens if the emissivity variation or an optical obstruction is too great and your errors become too large? Then we have to move to one of these advanced infrared technologies because these are able to compensate for emissivity variation. There are three advanced infrared technologies: two-color, dual wavelength, and multi-wavelength. And a two-color pyrometer and a dual wavelength pyrometer are very similar to each other. They're both called ratio pyrometers in that they measure infrared energy at two different wavelengths. The emissivity appears as a factor at each wavelength. And so when a ratio of the two measured energy values is taken, the emissivity appears as a factor at wavelength A, and it appears also as a factor at wavelength B, which means it appears in both the numerator and the denominator, and it cancels out. Now, the emissivity cancels out for a ratio pyrometer only when the emissivity is the same at both measured wavelengths. So the difference between a two-color pyrometer and a dual wavelength pyrometer is the technique that is used to divide the measured infrared energy into two separate wavelength bands. A two-color pyrometer uses a two-color detector. It's a two-element detector type where there's a top detector element and a bottom detector element. And that top detector element is sensitive to infrared energy over one wavelength band, but it's also partially transparent, allowing infrared energy of a different wavelength band to pass through. And so it's the optical properties of the infrared detector that dictate the wavelengths of measurement. For the two-color dual wavelength technique, the pyrometer includes a spinning filter wheel. And the filter wheel will have wavelength pairs, filter pairs on it that determine the wavelength of measurement. And so the big difference here is that with a dual wavelength technology, if you need to view through something that is transparent at some wavelengths and less transparent or non-transparent at others, like water, for example, or steam, then you can choose two wavelengths that view through water and steam equally well by selecting that dual wavelength technique. Whereas the two-color technique, you have to use the wavelengths that are coincident with the optical properties of the detector element. The other difference is that there's no separation between the two wavelengths of measurement for the two-color technique, whereas with the dual wavelength technique, the two wavebands have a distinct separation. Why is that important? Because when there's an interference for a dual wavelength pyrometer, it's much the same as a bump on the floor to a table. When there's a bump on the floor, your table will have a wobble. And if your legs are close together, then there's a big wobble. But if your legs are farther apart, well, there's still a wobble, but it's much smaller. So a dual wavelength pyrometer is about 20 times more stable when an interference is encountered compared to a tool color pyrometer. That means that an interference that would introduce an error of 40 to 60 degrees for a two-color pyrometer would be an error of only 2 or 3 degrees for a dual wavelength pyrometer. Now, as mentioned earlier, the two-color and dual wavelength technologies, they assume that the emissivity is the same at both measured wavelengths. And while the dual wavelength technology is less sensitive to this type of variation compared to the two-color, it still assumes that the emissivity is the same at both wavelengths. And the problem is for zinc and for cold rolled steel, there is a difference in emissivity versus wavelength. And that has to do with the microscopic surface texture of the metal. When the metal is really smooth, these little nooks and crannies that are present on the surface are small enough that the shorter wavelength can fit in better than can the longer wavelength. And what that means is that the material is more reflective at the longer wavelength and less reflective at the shorter wavelength. As you recall, emissivity is the opposite of reflectivity. And so because the reflectivity is different at the two different wavelengths, then the emissivity is also different at the two different wavelengths. The way a multi-wavelength pyrometer works is first it calculates a ratio measurement, and then using the information from across the wavelength set, it calculates a correction factor. In order to correct for an emissivity, it applies an E-slope adjustment, which is to a ratio pyrometer like an emissivity setting is to a single wavelength pyrometer. And it's calculating the surface character and applying a correction factor to produce the true temperature reading. We'll discuss that more when we get to that part of the presentation. Another advantage of using an advanced wavelength technology is because you're measuring multiple wavelengths, you have the ability to calculate multiple parameters. You know, if you're only measuring one thing, you can only calculate one unknown. Whereas if you're measuring more than one thing, then you can calculate two unknowns. So the advanced technology pyrometers, not only do they calculate a measured temperature value, but they also calculate a measured emissivity value. To calculate the emissivity value, they first calculate the temperature value, and then they compare the measured infrared energy with the black body energy at that same temperature. And the definition of emissivity is measured infrared energy divided by black body infrared energy. If they calculate the true temperature, then they will calculate the true emissivity. But if they calculate a false temperature, they will calculate a false emissivity reading. And so by monitoring the emissivity value and making sure that it passes the common sense test, that's one of the ways that you confirm that your measurement is accurate. Another thing about these advanced technologies is for customers who are accustomed to using single wavelength pyrometers, if you replace those with an advanced technology pyrometer, you may be getting a different temperature reading, which would render all of your recipes obsolete. And so what customers do is they put the advanced pyrometer, technology pyrometer, in the single wavelength mode, and they control the process off the single wavelength readings. But these pyrometers can operate in two modes at the same time. So while you're continuing to control the process using your familiar single wavelength readings, you're also logging what the multi-wavelength reading would have been so that you can update your recipes for the new values. And after 3 or 6 months of running with both modes, then you can create your new recipes and run using the advanced technology. So now on to the continuous annealing line measurements. There are 3 different areas associated with this process. There's the welder, the annealing furnace, and the zinc-coated steel strip. For the welder measurement, the complication here is alignment. The welder is not only a very small heated area, but there's a temperature gradient across its length and across its width. And what that means is, for a single wavelength or two-color pyrometer to measure a true temperature reading, you need to aim the pyrometer right at the center of that heated area, which means you need a spot size less than 3 millimeters, and it has to be precisely aligned. And the issue with this measurement is it's very difficult. If the alignment were to change even a fraction of a millimeter, then your temperature reading would change. Using a dual wavelength technology, you're able to view a relatively large area, one of 9 or 10 millimeters, or up to 3/4 of an inch, which is like 20 millimeters. And as long as that heated area is within that field of view, a dual wavelength pyrometer will self-align to that hot spot there, so that the reading does not change even as the pyrometer alignment varies. Now, when we go to measure inside the furnace, what we find is that we have two problems. The emissivity of the strip is variable, and the emissivity of cold rolled steel is nominally 0.35, which means it's about 35% emissive, but it's also about 65% reflective. So when the pyrometer views into the furnace, it's seeing about 35% strip and about 65% background. And if the background is hot, then that background temperature can interfere with the reading. So there are two different techniques that are used in order to compensate for these two different application issues: emissivity variation and hot background reflections. The first is the roller wedge measurement technique, and the second is what we call the direct view measurement technique. And we'll discuss both. For the roller wedge measurement technique, the pyrometer is aimed at the strip at a very shallow angle, so that instead of seeing a reflected image of the furnace background, it views a reflected image of the roll. And then off the roll, it views another reflected image of the strip, and then off the strip, another reflected image of the roll. So through these multiple reflections, every time it views a second surface, the effective emissivity is increased. So by having the pyrometer installed in this way and allowing it to view multiple images of the strip and of the roll, what you're doing is you're creating a near black body condition where your emissivity approaches 1. But the ability of that emissivity to approach 1 depends upon where you aim. So this thermal image of a roll and a strip coming together, this shows an apparent temperature change, but that's a false temperature change. What's really happening there is the emissivity is increasing as you aim closer and closer to that roller nip. And depending upon the angle at which you view, this sweet spot where the emissivity is essentially 1 will vary in size. If you're at a 5-degree angle above parallel to the strip, your sweet spot is pretty large, but your field of view is very elongated because of the steep angle. If you're coming in at a 20-degree angle, your sweet spot is really much smaller. So ideally, you want to come in at an angle between about 7 degrees and about 15 degrees. It creates a nice, good sweet spot, but your field of view doesn't become really, really elongated. But it's not only the angle from parallel to the strip that's an issue. sometimes the pyrometer needs to be installed off the center line of the strip. And when this is installed in this way, it's also important that the strip be wide enough to allow for all these multiple reflections, because for if you're coming in at an angle from the center line of the strip, then each successive reflection is from a different position along the width of the strip. If you don't have a wide enough strip to create an emissivity of close to 1, then what you need to do is you need to realign the pyrometer closer to the side where the pyrometer is mounted. And here we have a graph that shows exactly this issue. We had a customer that changed the width of the strip from 43 inches to 36 inches. That's a difference of only 7 inches, which is only 3.5 inches on half of the strip. In this case, the pyrometer was mounted directly at the edge of the center line of the strip. And when the strip width changed, there were 2 pyrometers, one installed in a wedge measurement and one measuring the strip directly. And when the width changed, the pyrometer measuring in the wedge position showed a 43 Fahrenheit temperature drop, whereas the direct view reading stayed steady within 1.5 degrees. This was because the strip wasn't wide enough to create a black body condition, and they solved that problem by re-aiming the pyrometer to nearer the edge where the pyrometer was mounted. Now, if you're using a single wavelength pyrometer, and if it's properly aligned to that roller wedge position, then it will measure a true temperature reading. You know, if the window is clean and you're properly aligned, and you really do have a valid high emissivity condition. But if you use a dual wavelength or 2-color pyrometer for this measurement, then the pyrometer gives you a measure of temperature, and it also gives you a measure of emissivity. And since it gives you this measured emissivity value, that gives you some insight as to the validity of the measurement condition and the alignment of the pyrometer. By monitoring that measured emissivity value, it gives you the assurance that the reading is accurate and true. Another way that you can test to confirm that your reading is accurate and true is to perform what we call the wiggle test. The right way to align a pyrometer to the roller wedge is to adjust the alignment until you peak the single wavelength reading, and when it's correctly aligned, you should be able to wiggle it. You wiggle it in any direction and the reading should not change. If the reading changes when you wiggle the pyrometer, then that is an indication that you're not creating a true sweet spot with a high emissivity. The other way to measure inside the continuous annealing furnace is with a cooled viewing tube, or what we call the direct view. And with the direct view, the pyrometer views down onto the strip, and it views the strip, as we said, it's 35% emissive, but it's also 65% reflective. And if the background is hot, then we need to make sure that the pyrometer is viewing a reflected image of a cold background in order to assure that the hot background does not influence the pyrometer reading. So the way we do that is to have a cooled viewing tube in those positions where the furnace background is hot. You know, if you have a cooling zone, then you don't need a cooled sight tube. The background's already cold. So in order for that cooled viewing tube to become an effective shield to prevent the pyrometer from viewing a reflected image of a hot background, the geometry has to be right. So first of all, the pyrometer needs to be mounted perpendicular to the surface of the strip. Secondly, the face that's of the cooled tube that is facing the strip needs to be large enough relative to the distance between the strip and the end of the tube so that it can prevent the view of the hot background. And the pyrometer views an area that's the distance divided by 2 in diameter, but then you have to add in the diameter of the field of view, and you have to add in some factor of safety. So basically, we typically recommend that these tubes be 2 times the distance plus about 100 millimeters or 4 inches to provide that factor of safety for the diameter of the viewing area and for misalignment. Well, here's an image that shows what that tube is doing, and as the tube shields an area on the strip from the hot background, but the shielded area is actually smaller than the diameter of the tube. And so it's not good enough for the pyrometer to be aligned simply to view through the tube. It must be aligned to view through the center of the tube. And again, how do you know that you're properly aligned? You perform that wiggle test. If you wiggle the pyrometer and the reading does not change, then that's a confirmation that you're aligned to the sweet spot. If you wiggle the pyrometer and the reading changes, then that's an indication that you're getting interference from a hot background. And for the advanced pyrometer technologies, the measured temperature value should remain steady, the measured emissivity value should remain steady, and the measured infrared energy level should remain steady. Now, that cooled viewing tube, it only solves half of the problems. It eliminates any hot background reflections. But what about emissivity variation? This graph shows the typical emissivity variation associated with various grades of steel. So the light blue circle there at the bottom, that's the typical range of emissivity variation that we would see with a stainless steel. The darker blue is with a cold rolled steel. The red is with hot rolled steel. And that green circle there in the middle, that's what we see typically from your high strength steels. So so as the emissivity scale is shown on the bottom of the graph, and then on either side of the graph is the temperature errors that are associated with that type of an emissivity variation. If we were to just assume that the emissivity is 0.45 or something like that, then that shows the error that you would get as the emissivity varies. So how do we compensate for this? First of all, if you run the same product all the time, and it always comes from the same cold rolling mill, and they always dress the roll for the cold rolling mill the same way, then maybe your emissivity really is pretty stable. But when you run different alloys, when you have different degrees of oxidation, if you get your product from different cold rolling mills, then there will be an emissivity variation even within the same alloy. The greatest contributor to emissivity variation is surface texture. And a lot of that has to do with how the roll is dressed on the cold rolling mill. So again, in order to correct for this emissivity variation, this is where your multi-wavelength technology comes into play. And a multi-wavelength pyrometer is loaded with an algorithm that understands the emissivity change with wavelength for the material that's being measured. And so a multi-wavelength pyrometer, it may have one algorithm for, I thought I had turned that off. for an aluminum surface. It may have a different algorithm for a zinc surface. It may have a different algorithm for a steel surface. And here's a view on the right-hand side. You can see on a microscopic scale that there is this surface texture on the surface of steel. That happens to be a high-strength steel, and what you're viewing there is the elemental silicon and magnesium, manganese, that has come to the surface and is oxidized. That's mostly manganese oxide there on the surface. And I don't know if you can tell on that scale, but that's about a 1 micron, if you can read that. There's about, we'll cover that again later. But the multi-wavelength pyrometer, without any adjustments, it does produce a repeatable and accurate reading on all these different grades of steel. And we talked about the wiggle test already. Now, there is a special consideration for those plants that run advanced generation 3 advanced high strength steel alloys. And that is because these oxides that form on the surface, they have this unique surface character, surface roughness associated with them, and they can cause an interference. When you look at this surface on the scale of the 1 micron wavelength, and that's that smaller square that's shown there, then depending upon where you view, the surface texture can be quite different. It can be a deep cavity, or it can be a lot of really small, it's kind of a smoother area. When we look at an area on the surface that's in the 2 micron range, which is represented by that larger square, then the variation on the surface is much more uniform. And so when we run this generation 3 advanced high strength steel, what we find is that when we use the shorter wavelength set, we get an indeterminate condition, and we don't always report the true temperature. Whereas when we scoot out to the longer wavelength, that allows us to make a true temperature reading, even when we're running these advanced high strength steels. So for plants that do run generation 3 advanced high strength steels, you do need to use the 20 wavelength, a wavelength longer than 2 microns in order to produce a true temperature reading. Now, the 10 wavelength set, which is using wavelengths closer to the 1 micron range, that wavelength set is much less sensitive to warm background reflections. So you can use a pyrometer in the 1 micron range, even in a soaking zone, without having to use a cooled viewing tube. But when you use a 20 wavelength set, it's much more sensitive to warm reflections. And so you would need to use a cooled viewing tube with that. If you're running a generation 3 advanced high strength steels, you'd need to use a cooled viewing tube in places where you wouldn't need to if you weren't running that alloy. Because the multi-wavelength pyrometers do provide a measure of emissivity, they do also provide some feedback for plants that are purposefully creating a layer of oxide on their advanced high-strength steels. You can monitor the oxide layer going on, and you can monitor the oxide layer coming off by monitoring the measured emissivity value. Now we run into some issues. For plants that don't trust their pyrometer readings, they tend to control the process using a computer-based model or by monitoring the temperature of the atmosphere rather than the temperature of the strip. And when you do this, a model is unable to account for real-time changes in the emissivity of the strip. And particularly in the heating zone, the efficiency at which the strip is absorbing heat in a direct fired heating zone is directly proportional to the strip's emissivity. Remember, emissivity is the opposite of reflectivity. So as the emissivity of the strip changes, its ability to absorb that heat also changes. So you do get better process control by controlling directly to the strip temperature, or if you're using a level 2 control system, at least to use that measured strip temperature very heavily in your process control. One of the things that we see from a poorly controlled line is temperature oscillation. And this type of temperature oscillation can be the result of a disconnect between the speed of response of the control system to a change in temperature. So in this case, what you're seeing here, this variation in temperature, is related just to the fact that the time constant associated with the speed of response of the control system is out of sync with the time constant of the ability of that same system to introduce a change. So this is more related to a time constant type of a variation. But we see this same type of oscillation when customers are controlling to a roller wedge measurement. What will happen, and I apologize, this graph, maybe it isn't quite so clear, but the strip temperature is represented by the black line, responds more quickly to a change in step temperature than does the roll temperature, which is represented by the red line. So when there's a step change in the temperature, and particularly at the beginning of a startup, the roller wedge measurement is an average between the temperature of the roll and the temperature of the strip. But the strip is responding quickly and the roll is responding slowly. And so when you control to the roll temperature during a strip change, you are actually introducing an oscillation in the strip temperature, because once the roll, once the control temperature reaches the set point, what happens is the strip is there first, but then the roll temperature takes time to get there. And so then when the process gets, when the roll temperature starts to cool, it causes the strip temperature to rise. When the strip temperature rises, it causes the roll temperature to cool. And so you do get this, this oscillation that can occur when you're controlling to the roller wedge for a strip change. So this type of an oscillation is eliminated by controlling directly to the strip temperature rather than controlling to the roller wedge or atmosphere temperature readings. Again, in both cases, it's caused by a difference in the time. It can be a difference in an artificial difference in the time that's induced simply by the time constant of the control system, or it can be a true difference in the time response of a roll and a strip to the same step change in temperature. So here we have a decision tree, if you would, for selecting the best infrared technology for a continuous annealing line measurement. So your first question is a roller wedge measurement position available? And is the geometry adequate for producing a high emissivity reading? You use a dual wavelength pyrometer to measure the emissivity, and if the emissivity is above 0.94 and stable, that's a valid roller wedge measurement. Then, if you're concerned about the speed of response to a step change, well, then maybe the roller wedge measurement technique isn't the way to go. But if you're not so, if you don't have a lot of step changes in your process and you're not so concerned about the speed of response, then you can continue to use the roller wedge. Then are you concerned about alignment and dirty windows? Well, if alignment and dirty windows are not a concern, you can use a single wavelength pyrometer. But if you use a dual wavelength pyrometer, it will give you feedback confirming your alignment and a clean window. Now, if The roller wedge measurement technique's not available, or if the measurement conditions do not produce a stable emissivity value higher than 0.94, or if you are concerned about speed of response to step changes, then you'll want to make a direct view reading. And if the background is hot, then you need a cooled viewing tube. If the background is cold, then you don't need a cooled viewing tube. But if you don't use a cooled viewing tube, or rather if your background is warm, then you need to be concerned about, am I interested in a true emissivity reading, or am I using that 20 wavelength set? Then you'll need a cooled viewing tube. You'll need a cooled viewing tube. If you're not concerned about an accurate measure of emissivity, if you're not concerned about, if you're not using that longer 20 wavelength set, then you don't need a cooled viewing tube. Now moving on to zinc-coated strip. We're going to cover the galvanneal furnace, cooling tower top turn roll, the down leg cooling measurement, the temper mill measurement, acrylic coatings, and passivation dryer. The issue with the galvanneal furnace is that the emissivity of the zinc-coated strip undergoes a 10-fold change in emissivity between the beginning of the process and the end of the process. At the beginning of the process, the emissivity can be as low as 0.08, and at the end of the process, it can be as high as 0.8. So if you're trying to use a single wavelength pyrometer, you're just not going to get the accuracy that you need during this transition. Similarly, a dual wavelength pyrometer, if you set it up to measure accurately before the solidification, then after the solidification, you've got these big errors. But the multi-wavelength pyrometer, it cannot recognize the change in the surface texture between the highly reflective material at the beginning of the process and the more dull material at the end of the process. As you can see, even viewing completely through the transition phase, the average variance for the multi-wavelength reading compared to an embedded thermocouple in this offline test was a 1 degree difference Fahrenheit. And the standard deviation was only 2 degrees Fahrenheit. So for the galvanneal furnace, we do recommend the multi-wavelength technology. It will produce an accurate measure of temperature before the freeze line, after the freeze line, regardless of the position of measurement. And here's an example of some data that one of our customers shared with us. Here we have their model was predicting what the temperature should be, and they're comparing that to the temperature value measured by the multi-wavelength pyrometer. As you can see, there's a direct correlation between the two with an R-squared value of 0.975. You can't get much better than that. Now, regardless of the type of zinc-coated strip that's run, the strip goes up to the cooling tower to the top turn roll. And before it reaches that top turn roll, it must be cool enough to prevent galling of the surface, to prevent pickup on the roll. So temperature measurement at that top turn roll is quite common. Now, remember, if we use the roller wedge technique at the top turn roll, that roller wedge technique is an average between the temperature of the strip and the temperature of the roll. And in this case, well, the roll is not heated, it's only heated by the strip. So the roll and the strip are just not the same temperature. So you get a more accurate temperature reading, actually making a direct measure of the strip than you do by using the roller wedge technique at the top turn roll. But you have to use the right technology. If you're running galvanneal and any of the other zinc-coated products, then your emissivity is going to vary at that position depending upon which material you're measuring. So you can use a short wavelength pyrometer at the top turn roll and you will get excellent results because the emissivity doesn't vary that much as long as you know which material you're running. So if you have the ability to send an emissivity setting of 0.7 when you're running galvanneal and 0.1 when you're running any other zinc materials, you will get an accurate reading with a short wavelength pyrometer. If you are running, if you're not running galvanneal, then you can use a short wavelength pyrometer. It will give you an accurate result with an emissivity setting of 0.1. But if you're running them both and you don't have the ability to send it the right emissivity at the right time, just put a multi-wavelength pyrometer up there and it will automatically compensate for the change in emissivity. And not only will it measure the true temperature, but it will also measure the true emissivity. And then you can use that measured emissivity value to send to your other pyrometers on the down leg. So again, on the down leg cooling, here the temperatures are too low to use the multi-wavelength technology. A multi-wavelength pyrometer will not measure in the temperature range that's encountered on the down leg. But if you have a multi-wavelength pyrometer at the top turn roll, you can take the emissivity value that's calculated by that pyrometer and you can feed it to single wavelength pyrometers on the down leg. Or if you know when you're running galvanneal and when you're not, then you can send the right emissivity setting to the short wavelength pyrometer on the down leg, and it will automatically produce a true temperature reading. The only complication about the down leg cooling is for plants that use a water to cool the strip. Some plants use like a water spray, water mist. You can get steam. And for this reason, we recommend a pyrometer that's filtered in the 2.0 to 2.4 micron range. And that's because at that wavelength, the infrared energy passes right through steam as if it's not even there. Most low temperature short wavelength pyrometers, they use a slightly longer wavelength set that goes out to 2.6 or 2.8 microns. And those longer wavelengths, they don't view through steam. The next measurement point is the temper-mill entry. And again, here at the temper-mill entry, the temperature is too low to use a short wavelength pyrometer. So you have to use a long wavelength pyrometer. And in this case, we do recommend that you use the roller wedge measurement technique whenever possible. Now, again, remember, if you're not using the roller wedge technique, the pyrometer's aiming at the strip, and in the case of a zinc-coated strip other than galvanneal, that strip's 90% reflective. The emissivity is 0.1, which is 10% emissive, but it's 90% reflective. So it's like taking a picture of a mirror. And because the strip is such a low temperature, even the background of the building is considered a warm temperature compared to the temperature of the strip. So if you don't install your pyrometer in the roller wedge measurement technique, then the reading is being influenced by the temperature of the background. A pyrometer filtered in the 7.9 micron range, which is a pyrometer that's typically used for the measure of plastics. A pyrometer can be used. If you're unable to use the roller wedge measurement technique, then I strongly recommend you use a pyrometer in the 7.9 micron range rather than 8 to 14 microns, because that shorter wavelength is 4 times less sensitive to changes in the temperature of the background compared to an 8 to 14 micron pyrometer, which is like a general purpose wavelength. For strips that are coated with an acrylic coating, again, if you use that 2.0 to 2.4 micron wavelength, the acrylic coating is highly transparent at that wavelength. If you use a different wavelength, then the acrylic coating is only partially transparent, and the emissivity of the strip will vary depending upon the coating thickness. And so you really must use a wavelength 2.0 to 2.4 microns if you want an accurate measure of an acrylic coated strip. Otherwise, again, you need to use a roller wedge technique. And for the passivation drawing of an exit, again, a short wavelength technology can be used for this measurement, but it only measures down to about 74 degrees C. It won't, which is like 175 F or something. You cannot measure near ambient temperatures using these short wavelength technologies. But with the short wavelength, we can measure down to about 175 degrees Fahrenheit. And that's typically low enough for the passivation oven. And that is my time. This is a summary slide that reviews the technologies that are recommended for each of the measurement points. I've kind of zipped through the presentation as quickly as I could. And that brings me to any questions that anyone might have. Thank you.
All right, thank you, Thomas. I would like to thank Thomas for a very informative presentation. And we do have a couple of questions. The first question is, what would your recommendation be to measure the strip temperature at the top roll for GI and aluminized, considering that grain size of the coating may change and that the general ambience temperature is a maximum of 60 degrees C?
Right, again, at that top turn roll, you really need to use a short wavelength pyrometer, and that wavelength, it's typically the 2 micron range. And it's not that the emissivity doesn't change at that wavelength, but it only changes about 20%. So your emissivity can vary between 0.080 and 0.12 in that for that product mix. But at those temperatures and using that short wavelength, you really get some relatively small errors if you use that short wavelength. So a pyrometer filtered in the 2 micron range will make that measurement quite well. Or you could use the multi-wavelength. The multi-wavelength gives you more accuracy, but it's significantly more expensive. So typically, if you're only running galvanize and if you're only running galvanneal and galvalume, then you can get away with a single wavelength pyrometer. You get a few more degrees of accuracy with the multi-wavelength, but I mean, it's more than twice the price. If you're using galvanneal and any of your other zinc-coated materials, most people do choose the multi-wavelength technology.
Okay, Thomas, we have a follow-on to that same question, and it's regarding the hot environment. Do you confirm you need a water-cooled tube as well as the shield face?
Typically, you don't need a water-cooled tube up at the top turn roll. You can get some very high temperatures up there. The heat from the pot, it will rise. It rises like in a column, and that it'll float around, and you can get some really hot temperatures up there. So we do recommend actively cooling the pyrometer itself, but you don't need to have a cold background in that area because the strip is still significantly hotter than the surroundings.
Okay, we have another question. What is for you the disadvantage of the wedge technology?
Right, so the greatest disadvantage of the wedge technology is that you're really taking, there are two, you're taking an average temperature of the strip and the roll. And so what that means is that when there's a change in temperature, the strip changes much more quickly and the roll changes much more slowly. And so if you have a change in the temperature of the process, there's a delay there between the time that the change is made and the time that the change actually occurs. And customers that have switched from roller wedge control to direct view control, they've reported as much as extra 80 tons per shift just by switching to direct control. It has to do with the time that it takes to compensate for a step change in temperature.
Okay. We have
If you have a process and you never change your operating temperature, then the roller wedge technique works perfect. No problem.
Sorry for stepping on you there, Thomas. We do have one more question here. It says, how are the pyrometers calibrated online?
Well, online, what you typically remove a pyrometer to verify its calibration, but particularly for the advanced technology pyrometers, because they measure both temperature and emissivity, you can monitor that emissivity value as a confirmation that your temperature readings are good, because if the temperature reading goes out of calibration, then it's going to calculate the wrong emissivity reading. So the two things that we monitor for pyrometers that are online is we monitor that measured emissivity value to make sure that it is what it's supposed to be or what it historically has been. And then we also perform the wiggle test. So if you wiggle the pyrometer, just change its alignment ever so slightly, then none of its readings should change. Those are the two things that we can do online.
Thank you, Thomas. If anybody has any follow-on questions, you can submit them in through the question and answer element. And we do have one that just popped in. Which pyrometer is the most accurate in galvanizing furnace, radiant tube furnace?
Yeah, again, it depends upon the measurement technique. If you're using the roller wedge technique, then we recommend the dual wavelength technology. And if you're using the direct view technique, then we recommend the multi-wavelength technology.
Okay, folks, we are running over time just a little bit, but we have one last question that was just submitted. How to manage the strong variation of emissivity of hot rolled?
Right. Again, because the emissivity varies, the single wavelength technology is really not appropriate, particularly if you're using a direct view technique. So the roller wedge measurement technique is designed to correct for emissivity variation. And if you're able to use that roller wedge measurement technique, then we recommend the dual wavelength technology just because it gives you that verification of an accurate reading. But if you have to measure directly, then you really must use the multi-wavelength technology to compensate for the changes in emissivity, whether it be hot rolled or cold rolled, whether it be common alloys or advanced high strength steels. The multi-wavelength is recommended for the direct view measurement technique.
Okay, folks, we do have a couple of more questions that came in, but as I mentioned, we're over time. So we're going to pass those on to Thomas. He will follow up with you with those remaining questions. And I would like to turn it back over to Ken Landau right now from AIST.
Thank you, Greg. Thomas, a great presentation. Thank you very much. And Greg, thank you for moderating it. The screen up here. Just let everybody know that was by the sponsored by the Galvanizing Technology Committee. And our next webinar is one heat pot balance to check entry strip temperature. And that will be by Michelle Dubois. And that's March 11th at 11 a.m., similar timing. And as always, there's more details on aist.org. I'd like to, again, thank Thomas and Greg. And we will conclude the webinar. Thank you all.
Thanks, guys.
Have a good day, everybody. Thank you for your participation.